Welcome to lesson 2 of Math 3. In this video we're going to look at directed and weighted graphs, and we're going to look at some nice algorithms to walk through a graph and later on to walk through a tree. The depth first and the breadth first algorithm. The book is chapter 8.6 and chapter 9.1 and .2. Okay, some small definitions. What is the distance between two vertices, written as DUV, is the length of the shortest path between the two vertices. So, for example, if we look at BF, so we have this vertex B, and we have to go to F, then of course we could take the long route, going to D, C, A, E, F. But of course we choose the short path A, E, F. And so the shortest path we can do to get from B to F has length 3. It has 3 edges. That's the distance. The diameter is about the complete graph G. And then we just look at all shortest paths, or all distances, and then what we find is the largest shortest path. So for instance, if we would look at AB, that has distance 1, AEF, so AF distance 2, and that's the shortest path. ACDB, that would be 3. So we have to choose all combinations of vertices and then see what gives us the longest path, and that would be in this case the HF E, A, B, D. So to go from A to D with the shortest path would be 5, and that is in fact also the one with the maximum shortest path. In a weighted graph we add some information to the edges. So the edges are not all the same, but they have a weight or a length, just what you like to call them. And for instance, if we say AB has a weight 4, let's say it's 4 kilometers to walk from A to B, and it is 1 kilometer to go from A to C, and 2 kilometers to go from C to B, then the shortest path from A to B, so the shortest path from A to B would not be the edge AB, but would be A, C, B. Because from A to B it would be 4 kilometers, but from A to B via C it would give you 3 kilometers. So if you take a weighted graph, then there is some extra information taken into account, whether you should go to the direct edge or via a small detour, which would be even more efficient. So if we would look at this example with weights given to the several edges, then the length, for instance, of a path in this weighted graph is just equal to the sum of all the separate lengths. And so, for instance, if we would take the length of A, B, C, D, F and just add up all the weights, all the kilometers, all the lengths you have, and then you get a total sum. And the shortest path in a weighted graph is of course the path with the minimal weight. So if we look at this one, the shortest path from A to F, that would be 1 to C, 3 to E, 1 to D again, and 2 to F. And later on we'll talk about algorithms to do this with the help of a computer, so that we don't need to puzzle ourselves. If we have a directed graph, it only means that the edge can only be passed in one direction, and it's denoted with the arrow. So in this case we can go from U to V, but not backwards. It's just one direction into a graph. And of course, if we have a direction, then it is important which one becomes first and which one is last. So an edge normally was given like this, and then that is exactly the same as this edge. I don't mind, because you could go from U to V in that direction, but also backwards. But if we have a directed graph, then the order is important, and then we write it with round brackets. So U, comma V, round brackets. That means that U is first, and we can go from U to V, but not the other way around, a directed graph. And this is called an ordered pair, which we will also see in Math 2. V is also said to be a successor of U. So we start in U, and then the next in line is V. When is a graph called a directed graph? If we have minimal one edge with a direction. So we can have, for instance, this graph, and if only one has a direction in it, like this one, then it's already a directed graph. So minimal one directed edge. So we can only go in the direction of the edge. And so if we go from A to B, we cannot go to C, because this is not allowed. We can go from B to D, but we can also go from B to C, but we cannot go to C. So this red part is not correct. It goes into the wrong direction. You could, of course, this edge here, which is a normal edge with no direction, you could also write that as a double directed one, one from B to D and one from D to B. But you can see that it really clots our image. So if we can travel both ways, then we just omit the direction error and just write it as one edge. Of course, if we have a vertex with directions in it, then we can also talk about the incoming edges and the outgoing edges. So for instance, if we look here at this vertex B, then there are outgoing edges going to D and going to E, and there are incoming edges coming from A and from C. And we call these the in degree and the out degree. So the in degree of B would be 2, because we have one coming from A and one coming from C. And the out degree would also be 2, because we have one going to D and one going to E. And so for out degree D, we have one going to F, and that's it. And so only one out degree, and the in degree would be 1, 2, 3. Some special names, which you will also see in Math 2. If we have something which only has outgoing arrows, like this one, then this is a starting point of our graph, or a source. And if we get somewhere and that's the end of it, we can't travel any further. We have this F. I can't go back anymore. We call this a sink. It's the end of the story. We can't move on anymore. The overall degree is just a combination of the in degree and out degree. So just again count the lines, and then you don't worry about whether it's incoming or outcoming. Just add all the incident edges with this vertex. Okay, does a directed graph have an Eulerian tree? Then of course we cannot just check whether all the edges have an even degree, because if you look at this edge, for instance, yeah, you can imagine that we can never have a Eulerian trail from A ending in A, because A only has outgoing arrows. So I can go out of this one, but I can never go back. So then I can never have a Eulerian trail. So the only way we can have a Eulerian trail if the amount of in degree and the amount of out degree is the same for each vertex. So if I have a vertex D, for instance, then the number of outgoing edges and the number of incoming edges should be the same. That's in fact a translation of the degree is even in a directed directed graph. The incoming edges should be the same as the outgoing edges. And then we can find a Eulerian trail again. Okay, so far about these graphs and the directed graphs. Now we start with some nice algorithms. The breadth-first algorithm and the depth-first algorithm. Let's first look at it intuitive, and then we'll give you a way of doing this in a computer where we can use stacks and queues, as you probably already have seen in programming. We look at it intuitively, then breadth-first search means I scratch the surface and then go by layer by layer. And so I don't go into depth, but I do what is first to me, what is closest to me. So in this case, I go from A to B to C, F, E, D, and the last one. So I take layer for layer. If we would do depth first, then we start and we go as deep as possible. We just continue until we can't go anymore. And then we go back a little bit. Oh, we can go deep. We go back a little. Ah, lovely. We can go deep again. And then we just go back until we have the ability to go deep again. So you see the difference? So breadth first, layer by layer. And depth first, try to go as deep as possible. And if you can't go any deeper, go back, but only until you know, I can go deeper again. That's the difference of the two. Okay, let's try to make some algorithms up for them. And the algorithm for breadth first, we use a queue. And a queue is a first in, first out thing. If you're in a queue for a cashier in some supermarket, then when you're first in the queue, then all the people after you will also be served later. So first in, first out, that's a queue. And how does it work in this algorithm? So we start with the first element as a starting position, so that's this A, and we put it in the queue, first in, first out. So A is in the queue now. Now let me put it in the queue. And then I repeat. I get the first element of the queue, well, we only have one at this moment, and I process this element. And I look at all the neighbors of A. So in this case, I have two neighbors, B and C. And if a neighbor is not processed yet, and they are both not processed, then I put them in the queue. Okay, so this A is done, and I put in the queue, and I will put this a little bit down here. I put the neighbors B and C. Okay, as soon as we've done that, then we consider the first vertex in the queue. So in this case, that's B. I take it out. Okay, so A is already done. Next one is B. I take it out, B. And I check the neighbors of B. And this B has only one neighbor. That's D. And this one is put in the queue. Okay, lovely. He goes. And we take the next one, which was waiting for me in the queue. That's C. Okay, we take C out and we process C. And he has two neighbors, E and F. Put them in the queue. D, E, F. Okay, we take the next one from the first line, that's D, take them out, and we process D. He has G, H, and I, so G, H, and I. Okay, next one on line is E. I process E, well, there was nothing to do there, huh? It's, I can't add it. Then I take out F, no neighbors anymore. I take out G, H, and I. And now you see what is happening. So the total order I process it is first A, then B, C, this layer, then D, E, F, this layer, and then G, H, I. So by looking at it as a queue, so whenever I find something, I put it in the queue, and that means that he is next in line to be processed. I will get a nice breadth-first algorithm. And we can do this breadth-first search in two directions. So we can go from left to right, but we can also go from right to left. And what will help if you do it on the exam, and you'll make a sort of a table. So you start with the first one in the queue, and that one is ordered first. And then what is put in the queue are the ones, so let's do it from left to right again, B, C, that's it. Then the first one in the queue goes to the order, to the processing batch, and then in this queue the B goes, and what is added are the ones connected to the one is being processed at the moment. So that is D. Okay, then the first one goes again, and we process C, and C has EF, so that means EF are at the end of the queue, etc. And then you will see that it works just like we shown on the video. If we would do it the other way around, then we start with A again, but then added is C, B. C is processed, added is F, E, etc. It's exactly the same thing, only now we process from right to left. Let's look at another graph, now one with cycles, which is a more normal graph, just not a tree like we shown before. And we now asked to add neighbors to the queue in an alphabetical order. Okay, that's fine. Procedure is exactly the same. So we start with A, that's the one in alphabetical order comes first, and A is put in queue. Then we will take out A, and we process him, and the neighbors of A are B, E, and C. And they want us to add them in alphabetical order, so that means we add B, C, and E. So these are done. For your convenience, if it's a large graph, you can already put arrows, put crosses through them, and that you know that you don't have to do them anymore in the queue. You don't have to put them in the queue anymore. Okay, B goes out, so the next one is B. C, E are still left. We process B, and the only new one to add is D. Okay, done. Then we take out C, E, D are left, and C processed will give us F. Okay, and now you see we've already done all nodes, so now we can just relax and put the other ones in without having to check anything anymore, because we know it's done. And you see we have a very nice ordering of A, B, C, E, D, F. Breadth first. With the depth first search, we use a stack instead of a queue. And a stack, you know, if we have a stack and we place something on the bottom of the stack and something on top of it and something on top of it, then after, if we start processing the stack, we can only reach the top one. So a stack is also called a last in, first out. D is placed the latest on the top, but is processed the first. So, okay, how does this apply to our tree in this case, to our graph? We start with A. So we process A, and we choose a starting vertex. So we just take A and we put this one on the stack. And so let's make a stack picture of it. So A is on the bottom. Well, that's the only one in, so we take that one out and we process him. So A is the first in our ordered list. Then we process this vertex. Put it a little bit more there. So the stack is empty again. And then we look at all the neighbors of A which are not processed yet. So A is now out. And the neighbors of A which are not processed yet are B and C. Well, the stack is empty, so I just add B and C. Okay, B and C are in the stack. Then we take out the one latest put in, that's C. So in fact I can only cross it out now. We cross it out after it's processed in this case. So I've just erased the cross on B because it's not processed yet. So A and C are processed. So we have a stack B, C. C is taken out, gone. And we process C again. So on top of the stack we have E and F. And then mind this last line here. If we have a node that's already in the stack, then it gets on top of the stack. So then we delete the deeper one. In this case, that's not necessary yet. Okay, then we process F. So F goes out. We can cross out F. So, and we look at neighbors of F. Well, he doesn't have any neighbors anymore, which are not processed yet. So we take out E. E can be crossed out. And we look at non-processed neighbors. None. We take out B. And we consider non-processed neighbors. So that is D. So I'll make a new stack. D is in. D can go out. And we process G, H, I. Yeah, those are the last one in line. So I just take them out one by one. E, H, G. And that's it. Okay, let's do it again, but now choose our neighbors from right to left. So we begin with A. We process A, so we can cross it out. And we put in the neighbors of A on the stack. So from right to left, so that would mean C first in, and then B. Okay, we take out B because the right side is the top of the stack. So B goes out. We have C still left. We process B, and B only gives us D. Okay, great. Then B can be crossed out. We use D, take it out, and we process D, and that'll give us I, H, J. Great, D can be crossed out. Then we take out G. Nothing to be done. We take out H. Nothing to be done. We take out I. Nothing to be done. And then we are only left with C. So we take out C. And we add F and A. So F, E. And then we take out E and F. And we're done. Okay, so then the order is just A, B, D, G, H, I, E, F. So now we've done the same thing, but in the other direction. A depth first search algorithm, so go as deep as possible and then retrace. If we look at cycles, nothing changes. Okay, so we start with A. A is here and A can be out, and we process him. So we add B, C, and E. So in that order, B, C, E. And on the right side, it's the top of the stack. So we take out E. So that means this one is gone here, and we have still B, C left. And we add the neighbors of E, which are not processed yet. So that is D, C, and F in alphabetical order. So that means C first, then D, then F. And now you see we have a repetition of C, so the deepest one goes. Okay, we process F, F out, F, and we still have B, C, D. And the neighbors of F is only C, which is not processed yet. So we add C, the deepest one goes. Okay, then we process C, C is out, and he doesn't have any neighbors who are not processed yet. So that's it. We take out D, D, and then, yeah, nothing left to do, huh? Only B there. So that's B. So the order we get is A, E, F, C, D, B. And so very straightforward. Just do the same algorithm, but mind if you have something already there that you have to take it out of the stack and put it on top. Okay, nothing really changes if we try the breadth first and the depth first in a directed graph. A directed graph which has edges which may only go one way, like the one from A to E. Okay, let's just give it a go. So we make a table and we start with A, because we want to do it in alphabetical order. So A is processed, out it goes, and then we process the neighbors we can reach. And in this case we can reach B, E, and F. So they go on the stack. No, it's a breadth first, so they go in the queue, B, E, F. And it's a queue. So that means we take out the one we put in first, we take out first. First in, first out. So we process B, take it out. In the queue is still E and F. And then we check whatever node we can reach from B, which is E and L. So we enter E, but we already have that one, so just L. Then we take out E, it's gone, and we enter whatever we can reach from E, that is F, but we already have that one, so we don't enter it again, and that's it. Okay, then FL is left, we take out F. Okay, so F is gone, and from F we can reach D and D alone, so we add D. Then we take out L, and what can we reach from L? That is E. We have that one already, and we can do C. Okay, that's a new one. And we can do, no, that's it, because we can't do K, that's a one direction. So we take out D, etc. So in fact nothing changes. It's just a matter of now taking only those neighbors we can reach with the breadth first algorithm. You can finish this yourself and also try this directed graph with the help of a depth first algorithm. Nothing changes, only the amount of neighbors you can reach from a specific node is different. So, most important thing, if you have a breadth first search, think of a queue. If you have a depth first search, think of a stack. Okay, thanks. This concludes this lesson. I hope you enjoyed, and you can make the exercises. If you have any problems, don't hesitate to contact me.